Good day. I'm releasing this video as a means to further build on what was learned in class for those who might have missed the class or who want to listen to the explanation again to aid understanding, and also for carryover students. Generally, just a way of helping with your studies and preparation for exam. We started with wave energy, where we look at several very important concepts like wave power, wave intensity, the factors that affect wave energy. I've also considered numerical examples. Without further ado, let's move on. So this course look at the concept of energy of a wave. We need to understand the concept. Look at the factor that influences the energy of a wave. Then look at the various expressions for numerical problems and utilizing them, and also understand the physical implications of the parameters of the mathematical expression. That you look at what the parameter represent, the quantity they represent, that's what that means. It's good to understand it too. What is wave energy? We know that wave is a temporal disturbance that propagates through a medium. It's temporal because when such wave propagates, the state of the medium returns to equilibrium. So the medium is not permanently displaced. That's why I said to be a temporal displacement. And normally when wave propagates, there's usually transfer of energy and momentum from one point to another, usually from the source of the wave to any other point in the medium, depending on the direction of the wave. However, matter is not transported. Transportation is just of energy and momentum and not matter. That's why we said that the disturbance is temporal. So the matter in the medium itself is not. But there is transmission of energy from one matter to the other, to another, moving from the source or a point to another point. Therefore, a propagating or traveling wave possesses energy that is constantly transmitted by the wave. The wave would, however, be converted to other forms. And at times the wave could be destructive. We have examples, or we have seismic wave, earthquake that will lead to destruction of building. Then the wave energy is destructive depending on the soil and the vulnerability of structures built on such soil through which wave is propagating. So wave energy. Wave energy is the amount of energy carried by a wave, and it depends on its amplitude. You can see from that expression that the energy of a wave is directly proportional to the square of the amplitude of the wave. The energy is proportional to the square of the amplitude. The energy is proportional to the square of the amplitude. That is, when we have low amplitude, that means the energy is low. When we have high amplitude, that means we have energy is high. So a low energy wave is a wave with low amplitude, and a high energy wave is a wave with high amplitude. So in this low energy wave, we have more displacement of the matter or material in the medium, and here, so we have less in low energy and we have more displacement in high energy. We have more displacement in high energy. And the total energy of wave that is propagated or transported in the medium is given as the expression in equation 2, which is mil a squared omega squared lambda over 2. That's the total mechanical energy, where mil is the linear density of the medium. That is, medium, assuming the medium in one dimension, it tells you how dense, how much matter per square or per meter, how much matter per meter is present, how much material is in that medium. That's what mil stands for. Then A is the amplitude of the wave. Omega is the angular frequency of the wave, which is measured in radians per second. Mil is in kilogram per meter. The amplitude is in meter. The angular frequency is in radian per second. And wavelength, lambda, which is wavelength, is in meters. And this total mechanical energy is a product of the kinetic and potential energy of the wave. I represent kinetic energy as capital K and potential as capital U. So if you add both together, you have the total mechanical energy. Let's take examples of use of this. When you have a wave whose parameters are given as amplitude 10 meters, angular frequency 5 radians per second, the wavelength 3 meters, and the linear density as 7. R7 is 7 kilogram per meter. Now, what will be the energy of the wave? You will see this. You will substitute the total energy of the wave from the formula E equals mil A squared omega squared lambda over 2. Then mil is 7 kilogram per meter. Amplitude is 10 meter, square of that. Angular frequency is 5 radians per second, square of that. The wavelength is 3 meters divided by 2, and you have 26.25 kilojoule. Let's take an example. Calculate the energy of a wave with values, also given the amplitude, given the radian, the angular frequency, given the wavelength, and linear density of 50. Again, 50 is kilogram per meter, or else otherwise stated. However, even if not in kilogram per meter, you must convert to standard units. So you have your expression, and you solve to obtain 187.5 kilo. Now in this case, now you have to calculate the amplitude now. If the energy is 25 kilojoule, that's 25,000 joules, and the wavelength of the wave is 5 meters, and is propagating with an angular frequency of 10 radians per second in a medium of linear density 2. Again, that density 2 is in kilogram per meter. You have your parameters. But in this case, you have to calculate the amplitude. So you make your amplitude the subject of formula. And if you do that and you substitute the parameters given, you will have 7.07 meters as the amplitude of the propagating